The lens is a central component of computational photography. We've talked about lens characteristics in several episodes, notably episode 25 talked about ray tracing and geometric aberration, and episode 49 talked about the modulation transfer function and impulse response for a focal imaging system. This paper from Adolf Lohmann analyzes the scaling properties of lens systems. We first encountered Professor Lohmann's work in our discussion in episode 58, where we talked about the ambiguity function and his work on defocus aberrations. Here's a very insightful paper he wrote shortly after that, where he considered the trade-off between diffractive blur and geometric blur in lens imaging systems, and found that as scale increases, geometric blur tends to dominate. So here, this lambda f number has the same scale as we change this from a small lens to a big lens. Lambda f number doesn't necessarily change, but the geometric aberration, if we look at the ray tracing, that's independent of scale, and the geometric aberration gets larger. So this would suggest that the effective f number is going to be linear in scale, which is this plot that Professor Lohmann has here, where this is the space bandwidth product of the imaging system versus scale. And so when the scale is small enough, the diffractive blur is larger than the geometric blur, and diffraction dominates. But as the scale increases, the geometric blur gets larger than the diffractive blur, and diffraction doesn't matter anymore at some point, and the lens capacity does not increase as you increase scale, suggesting that there would be some maximum space bandwidth product one could achieve in imaging systems. Now, you can fight against this by making the lens more complex, as we'll see in just a second, which could suggest that you have a more relaxed scaling law, but you've increased lens complexity or decreased field of view in the system to try to accommodate for this growth of geometric aberration and the challenges of fighting geometric aberration as lens scale increases. This issue is particularly important in systems where you have to create a large space bandwidth product over a smooth, flat surface. The sort of seminal version of that system is photolithographic systems for semiconductor manufacturing. So here's a paper from 2006 analyzing the history of lithographic projection lenses. And the need for more and more complex lenses comes from the growth in the number of transistors per chip. So from 1980 to 2005, you went from a few tens of thousands of transistors per chip up to more than 1 billion transistors per chip. This trend continued. Here's a plot continuing that trend up to 2025. Recently, for AI circuits, there are single chips that have over 1 trillion transistors, so 1,000 times more just over the last 15 years. That's amazing, of course, and critically important to the growth of neural systems. This has been achieved through a variety of mechanisms. One is going to shorter wavelengths. One is going to more complex lenses that enable this kind of very large space bandwidth product needed to produce these kind of very dense circuits. But another aspect is just going to stepper systems, where you reduce the effective field of view or keep the field of view constant, and increase chip size by replicating the image over multiple areas. So there's a variety of ways that this trend has been enabled to continue. One has certainly been making the lenses more complex and more sophisticated. So you see from this is at the top lithographic lenses from the 80s up through lithographic lenses in the early 2000s. And here's a photograph of comparing the size of a lens from 1987 here to a lens from 2004. So these massive lenses cost millions of dollars and are increasingly complex. Now, here, we're not interested in photolithography, although we certainly benefit from better and better circuits in computational imaging. What we're interested in is image capture. So one way to increase the capacity of imaging systems is to make the lens more complex. But another way, as we'll talk about in today's lecture, is to parallelize the problem. And so there is a solution to overcome Professor Lohmann's limit by making the lens a parallel processing system. And this was done, for example, in the AWARE imaging systems through a DARPA program. Here you see here is a Aware 40, which has several hundred 14 megapixel microcameras. So each one of these little fibers comes into a 14 megapixel microcamera. That goes through a common objective lens over here on the left. Here's a picture on the right of the array of microcamera lenses. Here's a test image from this system, a wide field of view scene, and then zooming in on features in the scene. This system, I think, had about a 20 microradian IFOV, so one pixel resolved 20 microradians or somewhere in that range. You can interact with one of these images from the Aware systems yourself. If you go to this site on Gigapan, you can go and look at an image that was shot with one of the Aware cameras and zoom in and explore the image. This is, I think, just over a gigapixel image. The Aware systems were also used for video. So here's a video of a game between the Dallas Cowboys and Philadelphia Eagles shot on the Aware system. Here the pan tilt in zoom is all digital. The images, the camera's capturing the full field of view, which you recognize because you can not only pan tilt, but you can stop time and pan tilt. And so as the data flows, you have an interactive data set that you can work with and explore the world. This is an example of cameras growing in information capacity, just as chips have grown and other information technologies has grown. So the point of today's lecture is to talk about how lens design impacts cameras and how we can use innovative design to achieve very high pixel counts and capture the optical data cube. Computational Imaging. Episode 69, Lens Design. The introduction showed a plot of the number of transistors on a chip as a function of time, and we see exponential growth in that parameter. Here's a related plot of the floating operations in the largest supercomputers in the world since the early 90s through the present, and you see that it's improved by a factor of 1 million. Now, in the early 90s, we thought we had perfectly reasonable computers. There were supercomputers. The Cray machines were just coming to their sort of end of life. But since then, computers have improved by a factor of 1 million. That's amazing, but even more amazing is how cameras have not followed this kind of technology. Among all information technologies, cameras are like the least developed. Here we see one of the first digital cameras, the digital back, a Canon D1, which had 2.7 megapixels. Now Canon is selling full-frame cameras with 45 megapixels. That's certainly an improvement, but it's an improvement by a factor of 20, not an improvement by a factor of 1 million like we have with computing. Now, you may think that this is because cameras are limited by physics in ways that computers are not. We talked about this physical limit in the introduction that was discussed by Professor Lohmann. Here we see it again with a simple lens design in Zmax. Have a simple singlet lens. This scale is 20 millimeters, and you see this lens is not diffraction limited. And here's the MTF plot. The diffraction limit is somewhere here, and the actual MTF on the lens is down here. Now, if we change this lens, not by changing its shape or anything like that, but just change its scale, we go from 20 millimeters to just change the scale to 2 millimeters, suddenly the lens is close to diffraction limited. And this is this point about geometric aberrations scaling linearly with scale. So just by making the lens smaller, we can improve its F number substantially, or its effective F number substantially. So we talked in the introduction about ways to overcome this problem. The traditional solution is to make the lens more complex, as we saw with the lithographic systems. Here again is the history of lithographic lenses up to 2004, and you see this incredible amount of complexity entering the system in order to try to maintain a large space bandwidth product or an aperture limited space bandwidth product. At the same time as this kind of revolution has been going on, there has been a revolution in optics, and that's the development of the mobile device, the mobile cell phone. Here's a lens design from Largon with a 5-element aspheric freeform surface lens. Incredible complexity, and it achieves something like f2 sort of performance over, a small field of view, but in a very compact package. So the trend has been to try to make more compact lenses with faster f number rather than increasing space bandwidth product. Now, as we were talking about with the lithography, the real solution to increasing the pixel count on a chip is not just to make the features smaller, but also to use parallelism, to use stepper motors. When we look at this plot of the growth of supercomputing, really what happened here in the early 90s was the transition from serial, vector processing computers to parallel processing. So even extending here, of course, now that we have these 1 trillion chip neural processors, the transition from multiple core machines to neural processing can be viewed just as an increasing growth in parallelism in computing. This is a solution for optics, that if we use parallel processing, we can overcome the space bandwidth limits that were pointed out by Professor Lohmann and build cameras of increasingly high information capacity. So the central goal of lens design is not necessarily to get wide field of view, but to get the size, weight, and power of the system minimized, and especially the cost per pixel minimized in order to hit the resolution target that you have, and then you could use parallel processing to recover the field of view. So this paper from our group analyzes the cost per pixel of a imaging system as a function of the field of view. And so if you choose a certain IFOV, you'll find a minimum cost, and then you build lenses with that kind of scale, and then you can use arrays of those to create whatever field of view you want to get the kind of parallelism you want. Another way to look at this is in these multi-scale designs that were used in the AWARE systems. So the multi-scale designs use a spherical objective lens that's then shared by a parallel array of microcameras. The point of these systems, again, is parallel processing, just like we use parallel processing in computing, that rather than designing the lens to make the high-quality image everywhere, we can design an initial objective lens that collects the field from the object and gets the kind of angular resolution we want, but then we use arrays of microcameras to locally correct the field. And so this big difference between computational imaging and lithography is that we don't need a smooth field over a smooth image over the entire sampling surface. We can sample in different segments and then put the image back together. This allows us to parallelize the problem, reduce the complexity, and then this is MTF from this particular design of a Galilean multi-scale system, and you see that even here in this little ball, which is just 2 inches across, we get diffraction limited MTF over gigapixel scale images. So this kind of multi-scale design led to the super cameras that were discussed in the introduction, the AWARE cameras here with the QG quarter gigapixel and systems designed for 10 and 40 gigapixels. So this can be done. So we can go out and put cameras on the same kind of exponential information capacity growth curve as other information technologies. There's a couple lessons learned from building these parallel systems. First of all, one of the biggest challenges is focus control. The key aberration after you've built a system that corrects for the traditional Seidel aberrations is to try to get the image in focus everywhere. One of the key things to realize when you go out and collect large-scale images is that the focus and exposure and other image capture parameters will not be uniform over wide field with very high resolution. So you need to think about ways to focus. Now, one of the interesting things about this lens design is just by going to a spherical lens, you overcome some traditional aberrations, especially field curvature is limited as an issue because you have a spherical focal surface. But there's no way to focus a spherical lens without changing the radius of curvature of that focal surface. But by integrating focus into the microcamera array, you can focus locally in the field, and again, your goal here is to do this kind of local processing to capture high resolution data. So this is very important because it's just important to realize that it is possible to reimagine photography and really capture the optical data cube. Again, our goal is not to be limited by human imagination or human vision, but to think about how do we build cameras that capture all of the information that's present in the data cube, which means better spectral sampling, new ways to think about temporal sampling, and new ways to think about lens design. When you do that, though, you run into a problem. That's a lot of data. It turns out that the primary barrier to increasing information capacity of cameras is not necessarily the optics at all. It's really more on the information processing side. So here we have this QG camera putting out quarter gigapixel at 24 frames a second. That was going to a rack of computers that looked like this to process the data back in 2012. Recently, better and better camera ISP platforms and system-on-module processors from Qualcomm and NVIDIA have come out, and so you can take, instead of this rack of computers, cameras can go into these simple processing modules, and you can make more compact, more efficient array cameras. And so here's an example from a company that I'm affiliated with, Acuity, now Transformative Optics, that built a array camera. The black part here is the optics, the array of microcameras, and the silver part is the processing. You still see that the processing still takes substantially more space than the optics. So the path to better cameras is to follow a similar path to what we had with computing. That computing uses increasing parallelism and arrays of microprocessors. The path to better cameras in the near term is to make arrays of microcameras. So the cell phone has revolutionized imaging in the last 20 years by using integrated modules. For the last 100 years, the standard non-cell phone model for cameras has been to use removable backs with families of lenses. So we have here a family of different lenses that mount with standard mounts on digital backs. That path does not yield diffraction limited imaging systems working at f2 similar to cell phones. So cell phones can miniaturize the system by making sophisticated optics that are integrated with the sensor and work at f2. This paper referenced here goes through some designs to make longer focal length systems. So cell phones are limited to overall path length of around 5 millimeters. If we relax that and allow ourselves to make integrated modules that have very narrow field of view with cell phone style focus mechanisms, then we can make systems up to 60 millimeters, so 10 times the thickness of a cell phone, but still operating at f2. And then you use those in arrays like the Mantis camera, and you can produce gigapixel scale imaging systems. And so here's an example of going back to another football game of images taken with one of those Mantis cameras. And again, the camera is capturing the wide field everywhere. And then as you zoom in and out, you're just switching the data feed that you're looking at, not switching the overall. Nothing is mechanically moving in the camera. We're just zooming into our feed. Now, one aspect of this camera is it actually consists of also a heterogeneous array of imaging components. This paper from Light Science and Applications with Fang Lu and her group at Tsinghua University analyzed camera designs where we don't have uniform sampling. So another aspect of building large-scale imaging systems is we don't want the same focus, we don't want the same exposure everywhere in the field of view, but we don't necessarily need the same IFOV everywhere in the field of view, so we can have heterogeneous arrays of wide field, narrow field, multispectral cameras, and then put those together. And if we want to cover the actual information of the scene, this kind of unstructured multi-camera system will be much more efficient than a structured camera that you samples uniformly everywhere. Again, you see that here in this video from a Mantis camera. This is of the port of Dubai. When you're zoomed out, you're looking at just a wide field camera. And then when you zoom in, you switch camera feeds. This changes the way we think of data structure of images. We don't form a single stitched image. We have a data set that we're pulling. And so as you zoom in, when you see the image blur when you first zoom, that's because you're waiting to start the codec for the high resolution camera. These kind of cameras, of course, we just need to think of cameras as things like information systems where we want more and more information. There's diverse applications. You can have something like this where you only generate the data from the zoomed part of the scene, but we can also create scenes like this where here at the upper left we have a camera. There's the camera, and now I'm looking at it with the cell phone. As we walk up to the camera streamed live onto a display wall, You can see that this is a 100 megapixel camera and a roughly 100 megapixel display wall. Zoom consists of just getting close to the display wall. So you see here's the barcode, and you turn around, look across the room, and you don't see the barcode with the same resolution because you don't have the resolution that camera has to look at it with. So this is a new way to think about cameras, where we really push toward capturing the full data cube. Everything we've talked about in chapter 10 has been around we want to capture the actual spectral information in the data cube, we want to capture the actual temporal information in the data cube, and now we want to build information systems and lens processing systems that capture the full richness of the data cube. We have one more point to make in our discussion of sampling, and that is maybe in sampling the data cube we've been measuring the wrong thing all along. Back in chapter 8, we talked about measuring the coherence function and ways to beat the Rayleigh criterion by looking at the coherence measurements. Our final discussion about sampling strategy will be to look at maybe focal planes should be designed to measure the mutual coherence instead of measuring the irradiance.